tabular method of integration by parts is very useful for when you need to apply integration by parts more than once. Suppose I wanted to apply integration by parts to this problem over here. I could let u equal to x to the fifth and let dv equal to sine x dx. So I have u equal to x to the fifth and dv equal to sine x dx. du is equal to the derivative of this with respect to x, which is 5x to the fourth times dx. And to get v, I just integrate both sides of this equation. So I'll have integral dv, which is v, and that's going to be equal to the integral of sine x dx, which is minus cosine x. The integration by parts formula tells you that the original integral is equal to u times v minus the integral of v du. So that's going to be this times this minus the integral of this times this. And that's going to give x to the fifth times minus cosine x, which is minus x to the fifth cosine x over here, minus the integral of v, which is minus cosine x over here, times du, which is written over here. Now I'll take the original integral and I'll rewrite it over here. I'll take this term and I'll bring that term down. I'll take the minus sign over here and I'll bring it outside the integral, so I'll have a plus. I'll bring the 5 outside, so I'll have plus 5, and that'll be times the integral of x to the fourth cosine x dx over here. So what you've accomplished in going from here to here is to take this factor of x to the fifth and knock it down to a factor of x to the fourth. But it would be a lot of work to apply integration by parts 5 times to this problem in order to get rid of this factor and just be left with the integral of cosine x dx. For a problem like this, the tabular method can save you a lot of work. You have a table with 2 columns. You have this plus minus pattern on the left, starting with plus. This D column is for your du's. This D column is for your u's, rather, and this I column is for your dv's. You go back to the original problem, you choose a u again, so I'll choose u is equal to x to the fifth, and a dv, sine x dx again. So you write the u over here and the dv over here, but you don't have to write the dx explicitly. And in this column you just take derivatives, so you'll have 5x to the fourth, then you'll have 20x cubed, then you'll have 60x squared, then you'll have 120x, and the derivative of 120x with respect to x is just 120. And the derivative of a constant with respect to x is just 0. And when you get down to 0, you stop. This term over here represents your dv, so you have to integrate this term, and the integral of sine x is minus cosine x. Then the integral of minus cosine x is minus sine x. And then when you integrate this, you'll get a minus sign again from the integral of sine x dx, which will cancel with this, and you'll get cosine x. And then the integral of cosine x will give you sine x again. And the integral of sine x is minus cosine x. And the integral of minus cosine x will be minus sine x. And to actually calculate the integral, you go to this diagonal, and this line represents the operation this term times this term times the sine over here. So over here, that'll be minus from here, x to the fifth, from here, times cosine x. Then you're going to have this term times this minus sign. So that'll be two minus signs, which will give you a plus. And you just write down the next term, 5x to the fourth times sine x. Then you have this term times a plus sign, so you'll have plus 20x cubed times cosine x. And then you have this term times this minus sign, so you'll have minus 60x squared times sine x. Then you get this times this plus sign, so you'll have one minus sign, so you'll have minus 120x times cosine x. And then you have the last diagonal, which is this times this minus sign, so you'll have two minus signs, which is plus, and you'll have 120 times sine x. And when you get to the last line, you go across. And this line represents the operation of taking whatever sign you have over here and multiplying it by the integral of this term times this term dx. So over here, that's going to be plus the integral of 0 times minus sine x. This term times this term dx. And that's going to be the integral of 0, since 0 times minus sine x is 0. And the integral of 0 is just equal to a constant. And that's because the derivative of a constant with respect to x is 0. And here's the entire solution written out neatly, with this integral over here represented by this constant over here. Now what I'd like to do is take a closer look at the table. If I interpret a given line in the table as the sign here times the integral of this term times this term dx, then the first line is going to be the integral of x to the fifth sine x dx. But that's just the original problem. And this is u for the original problem, and this represents dv for the original problem. So since this is u, and when I go from here to here, I differentiate, this term is going to represent du for the original integral without the dx being written explicitly. And since this term represents dv for the original integral, and when I go from here to here, I integrate, this term is going to be v for the original integral. So now what I'd like to do is look at these two operations. Down this diagonal and then across. Now, this line represents the operation this term times this sign over here. But over here, that's going to be u times v for this integral over here, which is just written over here. So this operation is actually the first part of an integration by parts. Then this operation over here is the sign here times the integral of this term times this term dx. But over here, that's just going to be minus the integral of v, since this is v for this integral over here, times du, since this term times dx will give you du, and that's this term over here. So you can see that this operation and this operation together represent an integration by parts on the original problem over here. Now I'm going to rewrite this integral. And now you can see that this integral over here corresponds to this line over here. And at this point, the table is actually going to choose a u and a dv for you. This term over here is going to become the u for this integral here, and this term over here is going to represent the dv for this integral over here. And again, since this is the u for the integral, and when I go from here to here, I differentiate, this term is going to represent the du for this integral over here, without the dx being written explicitly. And since this term represents the dv for this integral, and when I go from here to here I integrate, this term is going to be the v for this integral over here. So now I'm going to look at those two operations again, down the diagonal and then across. And this operation is this times this minus sign, but this is u and this is v for this integral. So this operation is going to be minus u times v. But the minus sign is just because there's a minus sign in front of the integral. So again, this operation is just going to represent the first part of an integration by parts. And then this operation is going to be plus the integral of v du, since when I multiply this term by dx, I'll get du. So that's going to be plus the integral of v du for this integral over here. So that's just going to be the second part of an integration by parts. So you see again, and the plus sign in front of here is because you have a minus sign from the integration by parts, and there's a minus sign in front of the original integral. So again, this operation and this operation together are going to represent an integration by parts, and that'll be on this integral, which is the integral represented by this line over here. Now, if I look at this line over here, that's going to represent the integration by parts integral for this integral, or the second integration by parts integral starting from here. And this would be the first integration by parts integral here, and this would represent the second integration by parts integral. And if I were to look at that operation down the diagonal and the operation across here again, that would represent an integration by parts on the integral that's represented by this line. And you can continue that down to the bottom of the table. You can also see where this plus minus pattern comes from. You'll have this line and this line being an integration by parts, and that's where the minus sign comes from. That's the minus sign in front of this first integration by parts integral. And then this operation and this operation represent another integration by parts on this integral, which will give you another minus sign, but that'll be times this minus sign in front, so that'll give you a plus sign. And when you're over here, the pattern will just repeat itself. So it actually turns out that every line in the table represents an integral. and if it has a minus sign in front of it, it's minus an integral. So this line over here is going to be the original problem, and this line over here is going to be minus the first integration by parts integral, and this line over here is going to be plus the second integration by parts integral, and so on. And every step consisting of this operation and this operation together is going to represent an integration by parts. So if I'm over here, for example, and I go here and here, that's going to represent one integration by parts on the integral represented by this line here. Or if I was over here at the integral represented by this line, and I went here and here, that would represent an integration by parts on the integral that's represented by this line. So when you actually perform the procedure, you start off at the top, and that represents the original integral. You write down its u times v, but instead of writing down its integration by parts integral, you do an integration by parts on that, and you write down its u times v. And instead of going across here and writing down the next integration by parts integral, you do an integration by parts on that, and you write down its u times v. And you continue that down to the bottom of the table. And by doing that, you push the integration by parts integral all the way down to this last line over here. And in this particular problem, that would be this integral over here. And all these factors over here represent the product of u times v for successive integrals. So this product over here, this term over here would be u times v here for the original integral. And this term over here would be minus u times v for the first integration by parts integral over here. And so on for the rest of these terms. And this term together represent the final integration by parts here and here on this integral represented by this line over here. I'd also like to mention that when you actually carry out this procedure and you start from the first line, you don't have to go all the way down to the bottom of the table. You could start from this first line here and go down as many lines as you like. For example, you could start here and go down this diagonal, then this diagonal, then go across, and that would just represent two integration by parts. Or you could start here and then go down this diagonal, this diagonal, this diagonal, and then go across, and that would represent three integration by parts. And both those are perfectly valid mathematical procedures. The method is also good for certain self-reproducing integrals. For example, suppose I wanted to apply integration by parts to this problem over here. I could choose u equal to e to the minus x and dv equal to sine x dx. So then you put the u over here and you put the dv over here without writing the dx explicitly. Now I'd like to just apply one step in this procedure from here to here. So I have to take the derivative of e to the minus x with respect to x. So to do that, I have to use the chain rule. So first I take the derivative of e to the minus x with respect to minus x, and that's just e to the minus x. And then I have to multiply that by the derivative of minus x with respect to x, and that's just a minus sign. And then the integral of sine x is equal to minus cosine x. But now, what's represented by this line over here? This line over here would be minus the integral of minus e to the minus x times minus cosine x. Dx. And if you look at this integral, these two signs are going to cancel, so you actually have the integral of e to the minus x cosine x dx. But that's not any simpler than the original integral. So I'll go down one more step in the procedure. So I'll take the derivative of this, and I'll get a minus sign again. So I'll just have e to the minus x, since that minus sign will cancel with this. And the integral of minus cosine x is going to be minus sine x. And if I look at this line, that's just going to represent the integral of e to the minus x times minus sine x dx, which is almost the same as the original integral. So I'll try applying the procedure at this point. So you'll have e to the minus x times minus cosine x times a plus sign, and that'll be minus e to the minus x times cosine x. And then you'll have this times a minus sign, so you'll have three minus signs, which is just minus, and you'll have e to the minus x over here times sine x over here. And then you go across, and that's going to give you plus the integral of e to the minus x times minus sine x dx. So now what I'll do is I'll factor the minus e to the minus x from these two terms. So I'll have minus e to the minus x times cosine x plus sine x. And then I'll take the minus sign outside this integral. So I'll have minus the integral of e to the minus x times sine x dx. So now I have minus the original integral over here. So what I can do is just take this term over here, bring it to this side over here, and combine it with the original integral. So I'll have twice the original integral will just equal to this term over here, which is minus e to the minus x times cosine x plus sine x. And to solve for the original integral, all I have to do is multiply both sides of this equation by a 1/2. So that'll cancel out this 2 over here, and the original integral will just be equal to 1/2 this stuff over here. So I'll have 1/2 times the minus sign over here, which will be minus 1/2 times e to the minus x times cosine x plus sine x. And this is a solution to the original problem, but you don't get the constant because you took this integration by parts integral and moved it to the other side of the equation and combined it with this. So what you can do is just add the constant by hand. And this is the general solution to the original problem.